I wonder how we will ride in our expensive cars and ride bikes to work when there are no more fossil fuels. Are we going to use water as an alternative to fuel? I'm pretty sure you know why I'm saying so. Yes, our days are numbered with fossil fuels. Hi, I am Annussciah from Disaster Preparedness and Prevention Center ICOSA. Today I'm going to present my FYP research on non-catalytic production of biodiesel fuel from free fatty acid fraction of palm oil. The modernization in the lifestyle, the industrialization, and the rapid growth of population have been resulting in the increase in consumption of energy. As you can see in the figure on the left, crude oil, which is a fossil fuel, is the most used primary energy source in Malaysia. Transportation is one of the most energy-intensive sectors, mainly depending on petroleum products. Globally, the transportation sector is a major energy consumer and source of carbon dioxide emission. For 2020, it was estimated that the usage of diesel fuel for on-road transport in Malaysia would amount up to 7.04 billion liters, indicating a slight increase from the previous year. The world energy demand continues to increase. The growth will affect the stability of the ecosystems and global climate, as well as global oil reserves. Malaysia ratified the United Nations Paris Climate Agreement in 2015 to reduce the greenhouse gases by as much as 45% by 2030, which is in line to achieve the Sustainable Development Goals number 7, 12, and 13. The high cost of producing biodiesel fuel from renewable biomass resource is the primary obstacle to its use as a renewable fuel. To establish sustainable biodiesel fuel production technology, cost of production must be kept under control. Since edible oils are primarily used in the food sector, using them as a source of feed for the synthesis of biodiesel would be extremely expensive. In addition, the use of edible oil as a source of biodiesel fuel will indeed put this in competition with the food sector, leading to increased cost of production. The conventional method for production of biodiesel fuel from PFAD, which is palm fatty acid distillate and a byproduct of vegetable oil refinery, suffers from limitations when feedstock with high free fatty acids and water content is used in the conventional catalytic biodiesel fuel production processes. One of the alternative ways to overcome those global environmental issues due to dependency on fossil fuels in transport sector is by utilizing alternative fuels to petrodiesel. Use of biodiesel fuel is one way to reduce both the consumption of crude oil and environmental loading by greenhouse gases. Biodiesel fuel can be derived from renewable resources such as edible or non-edible vegetable oil, but it has been mainly produced from edible oils such as palm oil, soybean, and sunflower oil these days. The extensive use of edible oils for the production of biodiesel fuel could lead to so-called food fuel competition and results in a high cost. Therefore, solutions to overcome these issues are needed, and one of the solutions is to utilize low-cost feedstocks such as non-edible oil or waste cooking oils for the production of biodiesel fuel. Inedible fractions of crude vegetables oil, such as PFD, contained in large fraction in crude palm oil can also be used to produce biodiesel fuel. PFD is produced as a byproduct in refining crude palm oil to cooking oil. In 2021, crude palm oil production was 19.6 million metric tons and PFD production was 784,000 metric tons in Malaysia. PFD contains high amount of free fatty acids in up to 80%. Also, it is low cost since it is a low value added byproduct. The conventional method to produce biodiesel fuel from PFD is through trans-esterification process. This conventional technology is carried out under mild reaction conditions such as reaction temperature of 60 degrees Celsius and can yield FAME, which is a biodiesel fuel, at relatively low cost by using methanol and catalysis. However, there are some drawbacks in the conventional process, such as consumption of alkali catalyst in this process will cause reaction to happen in between the fatty acid contents and alkali catalyst by saponification, which reduces the yield of biodiesel fuel and this requires extensive separation and wastewater treatment. Non-catalytic production of FAME from PFD under subcritical water conditions is a potential solution to overcome the existing problems. What is subcritical water? Subcritical water is the water at higher pressure and temperature than the boiling point at 1 bar as shown in figure here. The temperature is in between 100 and 374 degrees Celsius and at high pressure, which is enough to maintain the water without vaporizing. Subcritical water treatment is an environmentally friendly and highly efficient method that does not require the use of an organic solvent or chemicals. Subcritical water requires less energy than the other thermal conversion processes which are operated at high temperature, such as supercritical methanol. The water is the sole medium in subcritical water process. The saturated hot water in subcritical condition has a very high ionic product and also low dielectric constant, which is why water behaves like an organic solvent and more reactive. No catalysts and chemicals are used. The water itself plays the role of catalyst and solvent in subcritical water conditions. Subcritical water method is very efficient for any refined oil as well as oil with high free fatty acid and water contents, which is a suitable non-catalytic method to produce FAME from PFAD. These are the objectives of my research, which are characterization, subcritical water treatment, and elucidation of biodiesel fuel production from PFD in subcritical water process and treatment conditions. The scope of my research work to achieve the objectives, PFD, which is the feedstock of non-edible byproduct in my research, was obtained from Sime Darby Oil's Langar refinery. PFD was characterized to determine its lipid and acidic fraction contents. Subcritical water technology as a potential alternative method was selected to produce the FAME from PFD, where water is used instead of chemical solution which plays the role of catalyst. The 2-liter band scale of subcritical water reactor was used in conducting the experiments in terms of limited temperature profile and maximum temperature, which is about 200 degrees Celsius. The restricted amount of sample for the extent of agitation bonds the scope of research. The variable parameters are temperature, duration time, and ratio of PFD to methanol to distilled water. Subcritical water technology was selected because of the fastest reaction time to yield biodiesel fuel, cleaner and also not costly compared to other conventional methods. How do we convert PFD to biodiesel fuel? This is my overall methodology. In this research, two different volumetric ratios, which are 1 to 2 to 1 and 2 to 10 to 1 of heated PFD to methanol to distilled water were used. The pre-mixed of the mixture were then treated using subcritical water reactor at predetermined operating conditions. After the subcritical water treatment, the products were transferred and left still at room temperature in a separatory funnel. In the separatory funnel, two layers were formed. The upper layer consists of FAME and unreacted PFD fractions, and the bottom layer consists of lower molecular weights fatty acids, water, and glycerol. The FAME layer was separated from the bottom layer by the decantation process and was poured into a 50 ml of centrifuge tube. The FAME produced was then sent for FAME analysis using gas chromatography mass spectrometry analyzer at this instrument setting given. Let's look into results and discussion. Figure 2 shows the effects of temperature and retention time on FAME yield at the volumetric ratio of 1 to 2 to 1 of PFD to methanol to distilled water. The highest FAME yield of 82.5% was obtained at 200 degrees Celsius at 15 minutes, and the second highest yield 79.9% at 140 degrees Celsius and 60 minutes. Coincidentally, the same result was obtained at the volumetric ratio of 2 to 10 to 1 of PFD to methanol to distilled water as shown in figure 3. The highest FAME yield was 88.1% and the second highest yield was 76.3%. At both volumetric ratios, the FAME yield tended to decrease at 60 minutes from 140 degrees Celsius to 200 degrees Celsius. According to researcher above, the convention of FAME is low at lower temperatures and it increases as the temperature shoots up. This implies that the conversion of free fatty acid is less efficient or possible side reactions of long-chain free fatty acids before the esterification to produce FAME. According to researcher Akin Falabi, esterification is a reversible reaction. Thus, applying an excessive amount of alcohol to the process might produce unwanted byproducts. Besides that, it is expected that an excess amount of water will be generated during the esterification reaction, which would then react with the feedstock, causing the process reaction to being reversible. The increase in the amount of alcohol to oil increases biodiesel yield and purity. Overall, the highest flame yield was obtained at the ratio of 2 to 10 to 1. The highest yield was 88.1% at 200 degrees Celsius at a retention time of 15 minutes. As a conclusion, subcritical water treatment is a potential technology to produce non-catalytic biodiesel fuel from PFAD. Also, biodiesel fuel from PFAD can reduce the increase in atmospheric greenhouse gases. It was demonstrated that FAME, which is a common but one of biodiesel fuels, can be produced from PFAD in the subcritical water process without a catalyst. The best subcritical water conditions which yielded the highest flame yield were at 200 degrees Celsius and 15 minutes at the mixture ratio of 2 to 10 to 1 of PFD to methanol to distilled water among the experimental conditions investigated. However, flame yield decreased significantly at the longer retention time at the same mixing ratio and temperature. This implies that degradation of flame produced had taken place. Optimization of subcritical water conditions and the mixing ratio is recommended for future studies. That's all from me. Thank you very much for watching my presentation.